Okay, so this will be the worksheet number 4 from the lecture number 4. So in this lecture, we discuss about actually two parts. First one is we discuss about kinetic energy, potential energy, work done, and then energy conservations and those things, right? And second part of the lecture 4 was about the momentum. Momentum also we discuss about the how to calculate momentum and also how to calculate impulse, and then we discuss about the momentum conservation. So now in first part, actually, I'm going to briefly summarize what we have done. So some basic definitions. So we discuss about the mechanical energy, right? So mechanical energy is basically divide we into two parts. One is the kinetic energy and second one is the potential energy. So kinetic energy is the energy of the motion. That means there should be a mass and velocity of the object. Then we can write the kinetic energy equal half mass and velocity power 2, right? So potential energy is the energy of the position. If you have an object in some height or some depth, you can write the energy of that object. That is the potential energy. So potential energy, actually we divide into two parts in the class. One is right here, and one is gravitational potential energy. I'm going to write potential energy due to gravity, right? And also we discuss the potential energy due to spring potential energy, right? So now gravitational potential energy means if you have an object, we'll say I have potential energy 0 at this point. Then if you have an object in this height, h height, then potential energy at this point, we call it as the mg and the h, right? But if you need to find the potential energy in some depth compared to your potential energy 0 point, here I have the potential energy, if this is h, m, g, and h, right? So potential energy due to gravity, we can define that. I'm going to extend this equal sign or make an arrow. This is the information about the potential energy due to gravity, right? And potential energy due to spring, that means if I have a spring that I keep it as it is, that is, we call it as the equilibrium. We say I have object in here, right? So now definitely I will be able to compress this spring by push the object in. I can make the object here. And also if I want to stretch it, I can drag the object, right? So you will see that your distance of the spring, displacement of the spring is different now. So we're going to take this as your equilibrium point. Then if you have a distance here, we'll say x, or the distance here you stretch x. In this case, it actually doesn't matter you compress or stretch. If this spring has a spring constant k, then the potential energy due to a spring will be half k and displacement and power 2. That's about the mechanical energy we discussed, right? In addition to that, actually we discuss about the work done, right? So work done, as we discussed earlier, that will be force and the distance and the angle between force and the distance, right? Simple example, if I have object here, if I push this object, if this object move d distance, then you have the work done force times distance, in this case cosine of 0, that will be just 1. That is the work done definition, right? In addition to that, after we discuss these mechanical energies, we were able to write the work done by using change of kinetic energy, or we can write it as negative change of potential energy, right? So in physics, when we use a lot of times, what is the change of something? Change of something is always, I'm going to write it for the kinetic energy, but that is same for any other quantity that we are talking as change of some physical quantity. And this delta sign we use for the change. So change of kinetic energy means kinetic energy final minus kinetic energy initial. All right. That's what we did in first part of the lecture 4. Basic summary of the things that we discussed. This is where that we're going to discuss those problems together. Okay. So now my first question is asking some simple calculations for you to understand the concept of the class. So first thing is asking what is the kinetic energy of 5-gram bullet traveling at 200 meters per second? Can kinetic energy be negative? Let's start with the first part. What is the kinetic energy of that one? So we know how to calculate kinetic energy. Kinetic energy will be half mass and velocity squared. It's very important that this mass you need to convert into kilogram. Everything should be in SI unit. Then your energy units will be joules, right? So now we can calculate this on 0.5 is half and time mass 5 grams. 5 grams means in kilograms how much? It is 0.005. We need to divide by 1000 to make it kilogram. So mass is 0.005 and then times velocity is in SI units 200, but never forget there is power 2 in the formula, right? So you're going to plug this into the calculator and then calculate your answer. I have around 100 joules. So that will be the kinetic energy of the 5-gram bullet that travel with 200 meters per second. Okay, my next question is asking, can kinetic energy be negative in some cases? Never. Why? Kinetic energy never be negative. Why the reason? Reason you see that mass will never be negative, half is never positive negative, and velocity, since velocity we have power 2, that always will be a positive number, never be negative. And what will be the units of kinetic energy? So we discussed that already. We know that it is joules, right? And we use the unit uppercase J for that. And then next question is it a vector? Explain. Kinetic energy is a scalar. Energy, kinetic energy, potential energy, whatever energy you have, energy is a scalar quantity. There is no direction for the energy. Okay. Okay, so that's it for the first question. Now we're going to do the same thing for the potential energy. Now, before the potential energy, it's asking another question. How much net work is required to accelerate 1000 kilogram car from velocity 20 to 30? Okay, so now that's the asking about the net work done. You remember that the work done, we can write after we learn the kinetic energy, we can write it as change of kinetic energy. That means kinetic energy final minus kinetic energy initial, right? So now, since we have the velocities, since we have the masses, we will be able to write it. Final will be when you have 30 meters per second, right? So that means mass is 1000. See that it is in SI unit already. I don't want the conversion in there. So 30 power 2 minus next term, kinetic energy initial. So again, mass still the same car and velocity is now 20 power 2. So you can plug it to the calculator, and if you have any problem with the answer, let me know. 2.5 times 10 to the power 5 joules. I write it in scientific notation. Okay, let me change color. Okay, so now my next question, can you can work done be negative? I mentioned that in your lecture also. Work done can be negative. When? So that means if you have a pause and the displacement in opposite direction, then your work can be a negative because it is multiplication of pause and the distance. So it is possible to be negative. Okay, can be negative, is possible. And then what will be the units of the work done? Work done has the same unit as the energy because it is change of kinetic energy. Then it is still energy of the units of the energy. And next question is asking, is it a vector? Explain. Work done is a scalar quantity, okay, similar to the energy. And if I ask what units, joules, right? So everything is fine. Okay, let's move into the question number 3. Now, by what factor does the kinetic energy of the car change when its speed tripled? So now I said the speed triple, but your question can be any different numbers, maybe twice, maybe half, maybe 4 times, right? That you have to do it yourself. So now let's do this question. We have kinetic energy equal half mass velocity square, right? So we'll say this is what you have initially, initial velocity. Now what you're going to do? Now you're going to change your velocity, final velocity, into 3 times of the initial velocity, 3 times of initial velocity. Now your kinetic energy will be, say, you can say 1 or 2 if you want. I write the final and initial. So you do not change the mass. Only thing you change the velocity, v final power 2. That means that will be half mass 3 times v initial and power 2. We'll simplify this, half mass v initial power 2, 3 times 3 is 9, right? So this is definitely kinetic energy initial, I write earlier, and this means this is 9 times kinetic energy initial. That means your answer is 9 times. Okay, so now let's move into next question. So next question is asking, you have the work done in bringing a moving car to stop. That information is important. You're going to stop it. Is the force of the tire friction is friction. This will be the stopping distance, right? So if the initial speed of the car is double, this is the next step. You're going to double the speed of the initial speed of the car, then what will happen to the stopping distance? So now by watching this one, what you can say, if you double the initial speed, definitely your car will be travel more than the car earlier travel, more than 5 kilometers. That is definitely understandable. But is that double or is that triple or 4 times? This is where that is coming from. You need to use the formulas to take a look on those, right? So now work done is the first thing is talking about. Work done is definitely, we discussed it is already change of kinetic energy. So that means, let's rewrite it, kinetic energy final minus kinetic energy initial. So now you need to understand kinetic energy final will be, you're going to basically stop the car, right? And kinetic energy initial is the where you have the velocity. Now I hope everybody understand in both cases, kinetic energy final will be 0 because you're going to stop the car, right? That means I have negative kinetic energy initial. This is definitely, I can write it as half mass and speed initially, whichever speed you start, right? So that will be equal to the, you know that the work done is another case, how to relate with the stopping distance. Work done will be force times the distance, right? That means I will be able to calculate again work done by using force and the distance that travel before stop. So that will be my final formula, right? So now this is the initial information, right? So, or you can say first case number 1, that is what happening. Case number 2, your D will be definitely changing because you double the velocity. When you double the velocity, V, you're going to change into twice of V1. Let's write this is as second velocity. Then what will happen? Half mass twice of the velocity squared, whole thing twice, should be equal to pause time your new distance. You did not change the pause, right? And here I have half mass V1 squared, but I have 4 times of that should be equal to pause times distance 2, right? So now I may probably make it a little complex, but what you need to think is your distance is actually proportional to the velocity power 2. That's why when I have a velocity v1 to the power 2, here I have twice of velocity 1 to the power 2. That will make 4 times of earlier velocity, earlier kinetic energy, right? So what that means is, what changes, since F did not change, D is proportional to the velocity squared. That's what I'm saying, proportional to the velocity squared. That means when you double the velocity, what will happen is your distance it will travel to stop will be 4 times. Okay, 4 times. I mean, it is, you can summarize as you understand, but this is the final answer. This is how you prove it. But if you know this step, then definitely it is enough for you to understand it is 4 times. Okay. Okay, so now next question is question number 5. So what is the potential energy of the 50 kilogram person in a skyscraper if he is 480 meters above the street below, right? So here is the street that you're going to say potential energy 0. This is where the person is sitting in height h equal 480 meters, right? We need to write the potential energy here is the one we need to write it as. So now potential energy in height, we know we can write force of gravity is mg, mass and the g value, and the vertical height h. Then we have all the information, we can just plug it. 50 kilograms, it is in SI unit. G value we already know, 9.80, and height is given in SI unit, 480. And then you're going to plug into the calculator and find the answer. I have 235 and kilojoules. 1 kilojoules is equal to 10 to the power 3 joules, according to our chapter number 1 units. Okay. And my next question is asking, can potential energy be negative? What will be the units of potential energy? Is the vector and explain. Okay, this is first part. And next part, potential energy can be negative. Yes, potential energy can be negative because you know that if this person is somewhere on the bottom, then where you decide your potential energy 0, and I have a negative potential energy in this area, right? Because of that potential energy possible to be negative. And next one is, what will be the units of the potential energy? Is still joules because it is energy, joules. And is it a vector? No, because it is an energy, it should be a scalar. Okay. Okay, let's move on to question number 6. So now we have a gymnast leave the trampoline, reach the maximum height of 4.8 meters from the initial point before falling back down. So you really need to understand what is going on in real life. So since it is given the maximum height, you need to read it carefully. Maximum height 4.m from the initial point. That means your trampoline is sitting somewhere here. That is connected to the ground. It's not talking about the ground. It's talking about with respect to this point, right? Then there is a person going to jump on this one, we'll say with some velocity, after he jump, trampoline will going to bounce up to some distance. And this is where you can label it as your initial and final. So now in this question, it is talking about the energy conservation. Energy is a conserved quantity. You can write energy in your problem anywhere, any position, energy will be a same or it is a constant value throughout the problem, right? That's what the energy conservation means. So now in a problem solving, what that means is you write E initial equal E final by choosing initial and final wherever you like, but initial and final should be match up with the given question, then it will be easy to solve. Okay, that's the idea. So, but after this person jump on the trampoline, what will happen? It will go up, but at this point, velocity going to be 0, then it is going downward again, up and down. That's how it will do simple harmonic motion or the back and forth or the up and down motion, right? So now we know that energy, we need to write it with the potential energy, initial plus the kinetic energy, initial. And this is final. I'm going to write on the same diagram because when you do the problem, it is better that you draw the diagram, kinetic energy, final, right? So now as soon as you write this one, you see that velocity at this point 0, that means this is going to be 0, right? So now if you take this point, because potential energy 0 is your definition that you can label anywhere in the problem to make it simpler, right? If I make potential energy 0 at this point, that means this part going to be 0, right? So now E initial equal E final, what we left at the beginning, I have kinetic energy, initial, finally I have potential energy, final. That means all kinetic energy initially I have on the trampoline, that person going to be converted into potential energy at the end, right? So now kinetic energy initial half mass velocity square, final will be mg, and the vertical height, say this height is h, right? It is given. So we can divide by m both side and then times 2 both side, then velocity square will be 2g and h, and that means velocity will be 2g, h, and root, right? Then you can plug the values. 2 and g is 9.80 and h is 4.80, and take the root of that. This will give you around 8 point, we need to put the calculator. Yeah, I have 8.4 actually, 8.4 meters per second. So what that means is if this person jump from 8.4 meters per second speed, then the trampoline will go to the height 4.8, right? It is not actually 8.4. Give me a second. I think I did the mistake. Let's put it in the calculator and see. Okay, we have 2 times. It actually 9.7. 9.7. Okay, so that's from 9.7. 9.7. Okay, so 9.7 speed will go to the 4.80 meters. But means if you have a lower velocity than this, that means this trampoline will not go that far, maybe stay somewhere here, right? So general idea is that. Okay, so now let's move into the next question. So I have 2 paths led to the top of the hill. One is steep and the other one is direct, right? So now what the question is asking, how much more potential energy would you gain if you take the longer path? Okay, so one will be deep. Another one will be like this, path number 1 and path number 2. So both going to land exactly onto the same height. So we'll say this is H. So now you can see it doesn't matter I took the path 1 or path 2. Potential energies depend on the mg and h. Since in both cases vertical height is the same, that means both are the same. There is no potential energy difference of these. Both are the same. Yeah. And let's go into the next question. So I have motorcycle cyclist is trying to leap across the by driving horizontally off the cliff. And so let's draw a little bit of the diagram. So we have this height and horizontally going to be go with some velocity. It's given after you are in this height. If you go in your bike in this speed, horizontally this is going to do a projectile motion. That means it's going to land somewhere here, right? So now it's very important in energy conservation, write initial and final first. So those are the initial and final. So now velocity is given here. I'm going to write V initial. When you come to here, so here is asking about the final velocity. I'm going to write V final, but V initial is given. You can write this as 38 meters per second. V final is the one we need to find it out. Always read the question very carefully. And vertical height is this height right here. This height is the vertical height. Let's label it as H. So now we're going to write the energies in these two places. In initial position, energy initial equal kinetic energy initial plus potential energy initial. When you label the potential energy, it's very important that you label where you choose your potential energy 0. I'm going to say ground is potential energy 0. Okay, so now E final here will be again kinetic energy final plus potential energy final. As soon as you write the potential energy 0 at this position, that means final potential energy is 0, right? So now we're going to write E initial equal E final energy conservation. So now initial energy, as we have kinetic energy initial plus potential energy initial, none of them are 0, right? I have both of them, but final I have only kinetic energy final. Now let's write down those formula of mass velocity initial power 2 plus potential energy mg and h is given. I'm going to plug it later, equal, and kinetic energy final half mass v final square. So now divide by m first both sides, right? And then multiply by 2 both sides. Okay, let's do that. Vi square equal 2gh equal v final squared, right? What I need is v final squared. So v final squared equal v initial squared plus 2g and h. Okay, now let's plug the values. V initial square is 38 power 2 plus and 2 and 9.80 and h is given as 100, right? And then find the v final. V final will be just root of that number. I'm going to do this at the same place since I do not have much space in here. Root and take the root of that. That will give you the v final answer. So I have 58.3 meters per second. Okay, so now next question number 9. Paul and John start from the rest of the same time frictionless water slides with different shapes. At the bottom, what can you say about their velocities and the time? Remember, same question. You have different water slides. So you're going to do the water slide, maybe like this, maybe like this, right? It doesn't matter. They're going to be jump into the pool at the end, right? This H is the same for both. So now what the question is asking, velocities. What do you think about the velocity? We'll say this is what the pole do, this is what the John do, right? So velocity of the pole on the bottom should be equal to the velocity of the John. Why? Because potential energy initially is converted into kinetic energy in here. Here I have a kinetic energy. Here I have potential energy. Potential energy for both of them are the same. Then the kinetic energy of the both of them are the same. If they have same mass, right, then they will land with the same velocity. They are the same. Okay. Okay, so now next question is asking, what can you say about their velocities and time? Time, what can you say? So definitely time will be longer for the John, according to, because John has bumps and the things that it will take longer time to travel. So in this case, if I do this drawing, John has longer time. Okay, now let's move into the D. How does the work required to stretch the sprint 2 centimeters compared to the work required to stretch it 1 centimeter? So now in this question, it is talking about the potential energy of the sprint, as we discussed in the summary, half K and the displacement power 2, right? So you have 2 centimeter and you need to compare into 1 centimeter stretch. This X at first time 2 and next time 1. Okay, so now when you stretch twice, this is twice, right? Twice. When you stretch twice, that means this potential energy will be X is changed into 2 times X. That means potential energy going to be 4 times of earlier. Okay, because X is changed into 2X in here, what will happen is potential energy sprint in new case will be half K 2X to the power 2. So that means this will be half K X to the power 2, what I had earlier. Now I have 2 to the power 2, that is 4. Because of that, that will be 4 times. Okay. Now 11, explain the difference between power and energy. What will be the units of power? Is it a vector? So now you remember that the definition of the power in the lecture, I discussed that power is basically energy per unit time. Okay. So that means energy per unit times means you have joule unit times is second. So that means joule per second is the units of the power, right? This is what we call it as watts. Watts or joule per second is the unit. Power is a scalar. Okay, scalar. Scalar quantity is not the vector. Okay, I think we discussed a lot of things together. So now we're going to move into the question number actually 12. Question number 12 is about the momentum. Because of that, I'm going to take a minute to discuss about the momentum. So momentum is the another physical quantity that we can say is the property of moving matter. We use the momentum symbol lowercase p that will be able to calculate by using mass and velocity. That means momentum is a vector that has the direction same as the velocity, and units you can see mass measured by kilograms, velocity is measured by meter per second, This will be the units of the momentum. Okay. In another way, this unit also will be able to explain by using Newton second, and we did it later. These two are equal to each other. Okay, so momentum is another conserved quantity if you do not do anything during the collision of the object, right? Then we discuss about the impulse a little bit. Impulse is basically force and time together. That means in another way, we can say this is force times time. Since if you think about the tennis racket, when the ball hit the racket, you know that it will be very short time interval. You are not able to even calculate the time, milliseconds. So because of that, sometimes we need to calculate these two things together. That is we call as impulse. Easy way to calculate impulse is change of momentum. So change of momentum means momentum final minus momentum initial. That's we call as the impulse. That also has the same unit as momentum, right? And then we talk about the momentum conservation and these things. Okay, let's move into the equation. Okay, starting from rest, two skaters push off against each other on ice where friction is negligible. There is two persons push each other. Push each other, right? When they push each other, what will happen is they basically have no velocity at the beginning because they're going to push each other, right? But after some time, you say that one is 55 kilogram, one is 80 kilogram. We'll say this is M1, this is M2, M1 is 55, M2 is 80. The 55 one moves away with the speed 2.5. V final, this guy has the V final that is 2.5 meters per second, right? And find the recoil velocity of the other one. This one, velocity we don't know, V final for the second person, this is first person, the one we need to find it out. So according to the mass, you definitely know 55 is lighter than the 80, then definitely my velocity for the second person should be a smaller value than the velocity we have on the first one. But this is where that we're going to use the momentum conservation. So they all have initial velocity 0 because both of them going to push each other. That means there is no initial velocity, right? So now we're going to write initial momentum equal final momentum. Initial momentum we're going to write for the system. This equation we write in for the system. Okay? That means both peoples in this case. So now initial momentum will be equal to 0 for both because momentum is mass time initial velocity. That will be 0 for the both of them as since I have the 0 in there. So now velocity for the both people, I have m second person and velocity final for the second person and minus velocity of the first mass of the first person and velocity of the first person. Now, why do I have negative in there? It's very important. Reason is that you see that I need to work with the direction. This is where my x direction that I'm going to say V final 2 is positive direction, but V final 1 is negative direction because of that first person has the negative moment. Okay, so now we need to find the V final 2. Let's write it, that one, and that will be equal to, you see that it will be M1 divided by M2 and V final 1. Let's plug those values. We have 50, 80 all ISI units and 2.5 given for the initial velocity. So this will give us a answer 1.7 meters per second. As we thought, you see that final velocity for 80 kilograms is lower than the person one. Okay, so I have few more questions. And number 13, when the speed of the object is double, its momentum will be. So now when the speed of the object double, what will be the momentum? So we do not change the mass. So you're going to double the speed. Everybody understand that momentum will be double, right? So P will be now twice of mass and velocity, double. There is no doubt, I think, double. It's a very linear connection that we can do. And momentum will be units of the momentum. We already discussed that, right? Unit is kilograms meters per second. That in another way, you can write Newton second. These both are the correct units. Okay, now is it a vector? Yes. It is a vector. Okay, let's move into the number 14. A small car and the large truck collide head-on and stick together. Which one has the larger momentum change? Is it a Newton third law? So keep it in mind what is the Newton third law is. Newton third law is you have equal and opposite force, action equal reaction. When there is action, there is a reaction. These are equal and opposite. That's what the Newton second law. Newton third law, sorry. Now, a small and large car going to hit each other. It doesn't matter which one is small or which one is larger. When they do the head-on collision, they definitely have the same momentum change. That means they have the force and the time. That means change of momentum. That means the impulse is the basically same. Change of momentum, equal impulse. That also equal force, time, distance is the same. For both objects. For both objects will be the same. Okay. Is it the Newton's third law? Yes, it is Newton's third law in another way. Okay, number 15. A small beanbags and bouncy rubber ball are dropped from the same height to the floor. They both have the same mass. Which one will impart the greater impulse to the floor? So now we have the bag. You're going to drop it, right? And there is a rubber ball. You're going to drop it. What is the difference between these two? When this drop with some velocity, it's going to stay and there. It is not bouncing back, right? But if it is the rubber ball, this going to bounce back with the same velocity. This is the ball. This is the bag, right? So now what happened is for the bag, change of momentum is equal. You see that the bag has the initial and final change of momentum is P final minus P initial. So now final is not bouncing back. That means this is 0. That means I have negative M and the V, right? But for the ball, what happened? Ball also has change of momentum. That will be P final minus P initial. None of them are 0. This final will be M and V, but initial will be negative M and V. Because of that, you're going to add twice of M and V. What that means is ball has greater impact. Greater impact. Oh, impulse is greater for the ball. Okay, I think I do have 2 more questions. Let's move into the 16. So box slide with the initial velocity on the frictionless surface. We do in always frictionless for the momentum and collide with the identical box. It's very important. Identical means this box mass M, this box is mass M. Twice means your box has 2 times of that. You need to keep track on those. The boxes stick together. That's another information. Stick together means both has same final velocity, right? Let's draw the diagram. You have a mass M of box and you have another mass M box. but it says at rest. That means this box is at rest. This box initial has velocity 10 meters per second. Okay. So now after they collide, you definitely know it's going to move in this direction and they hit each other. Then they're going to stick together and travel. Those informations are important. These two stick together and travel. They have the same velocity, V final. Okay, so now we know that we need to use momentum conservation. Definitely initial equal final, and everything on this direction will be positive. So now I'm going to write it for again system. That means both together. So now V initial, I have first object V initial only on the left object, because second object initial velocity is 0. That will be equal to now both of them. That means M also traveling with V final and other M also traveling with V final. That means this is twice of M and V final. Okay. So now I can calculate the V final by using this formula easily. So you can divide by the mass first. Let's bring this down. V initial equal to M V final divide by M both side. V final is equal to V initial divide by 2. It's very simple. 10 is given 2 and this is 5 meters per second. That means both objects are moving with 5 meters per second to the right direction. You can always make sure the direction is the right direction. Okay, last question. Calculate the impulse of the first object in the above question if the mass is 0.5 kilogram. So it's very important. Impulse only calculated for one object always. Only calculate for one object. Because if you calculate the both object according to Newton's third law, that will give you 0. That's why. Impulse only calculate for the one object. Now you need to understand it says first object is the one you need to calculate. Impulse is equal change of momentum. That means P final minus P initial only for the first object I am doing. Okay. So now this will be mass V final for that object minus initial object I have mass V initial. So now we have those numbers. We're going to calculate it. Mass is 0.5 times V final is 5 minus 0.5 mass and V initial given as 10. So now this definitely will give us negative number, definitely 2.5. What units is the units of the momentum, Newton second you can give. That's the final impulse for the answer. So it is asking what is the unit. I already give the units. Newton second. Is it a vector? Yes. Vector, this is the direction is right direction. I mean, since it is negative, you can say left direction, but if you write as a negative number, you need to say it's right. But if you, this is the two ways that you can write the answer. You can write 2.5 Newton second, then you need to write left. That's the idea. Okay, it's a vector. Okay, let's stop here.